Good evening, everyone. Hello. Hopefully, everyone are here. Hello. Today we will be seeing a bit of basics of real analysis. We won't even venture into sequences, but very basics of real analysis. So, can we start the proceedings? Hello. Hello. Is anyone here? Can we start the proceedings? Please. Okay, so I think you can start the session. So here today we will look into the basic number systems and the basic properties which govern this number system, and then we will move into uh, some properties of those number systems. Okay, so here we go. So, no, so before moving into number systems, let us see the hierarchy in which the number systems are present. So first, the first basic number system which everyone goes into is the set of all natural numbers. Now natural numbers consist of 1, 2, 3, etc. It is very much useful for us in counting. So this is the basic number system which exists by itself in the nature. This is a set of all natural numbers, and then comes whole numbers, which is a superset of natural numbers. It includes 0, 1, 2, etc. Then comes the set of all integers, where the set of all integers include 0, 1, minus 1, 2, minus 2, etc. Then comes the set of all rational numbers, set of all p by q, set of all numbers of the form p by q. where P belongs to Z and Q belongs to N, and GCD of P comma Q is 1. So this is how we are going to look into rational numbers in our entire lecture. So rational numbers is a set of all numbers of the form P by Q, where P belongs to the set of all integers, Q belongs to the set of all natural numbers, and GCD of P comma Q is 1. That is, we are considering 1 by 2 and 2 by 4 or 3 by 6, all are the same. Right? Then the set of all irrational numbers, this is set of all rational numbers, set of all irrational numbers. So irrational numbers does not have a specific notation, common notation. So this is all set of all numbers, set of all numbers which cannot be expressed as P by Q. And then we move into set of all real numbers. And if we go even more further, we will move into set of all complex numbers, etc. But we will move on in only till real numbers. So there is a hierarchy in which it goes. Natural numbers is a subset of whole numbers. Whole numbers is a subset of integers. Clearly, integers is a subset of irrational numbers. Sorry, rational numbers. These two are totally disjoint, and both of these are subset of real numbers. So now, so from our school days, we are used to represent real numbers on a number line. So what does number line say? Why does number line exist? And how does it exist? Are there any rules governing the number line? Now, what we do is, so whenever we draw the number line, so since it goes on, we put arrow marks at the ends. And say, suppose if you mark 0 here, we mark 1 to the right of 0 and minus 1 to the left of 0. And there are many numbers in between these two. Between 0 and 1 and between 0 and minus 1, if you consider it as a real number line. Now, so we are, by writing a number to the right of, by writing 1 to the right of 0, we actually mean that 1 is bigger than 0. So, say there are two numbers, say maybe maybe I will say those two numbers to be AB and they belong to real numbers. So, intuitively, by now, we know that either when we plot these two numbers on the number line, either they can be this way or they can be, sorry, I will better write it one by one. Either they can be this way or they can be this way, or else both can be the same. So both are A and B or both are A and B. That is, both are the same numbers. So there are only these three possibilities, and only one of these occurs. But who gives us the guarantee that this is always true? That is, given any two real numbers, either one is bigger than A is bigger than B, or A is smaller than B, or A is equal to B. So whenever you have the set of all real numbers, this property holds. That is, we call this as law of trichotomy. So what does law of trichotomy say? Law of trichotomy says that if a and b are two real numbers, then either a less than b or b less than a or a equal to b, and only one of these three possibilities occur. Exactly one of these three possibilities occur. But now there must be a question. What does this less than symbol refers to? Equal to is fine, both are the same, but what does this less than symbol refer to? So we need to define what is that less than. So whenever we have something in our hand, any law or any theorem, we need to know what are all defined there, and we need to know what all the definitions which are given in the statement. So we need to know what do we mean by a less than b. So we define an element to be 0. So we move into actually field theory a bit. We define 0, and what we do is we define some particular set of numbers to be positive numbers. So we split the set of all real numbers into 3. We split this set of all real numbers into 3. That is, R is singleton 0 union P, set of all positive numbers. So we name that to be positive numbers, and then the set of all others leftover numbers and real numbers. So we can call that as maybe say B. It is our convenience for now. So we split the set into 3 disjoint sets, set of all real numbers. So we define A less than B as A is said to be, if A and B are two real numbers, then we define if A and B are two real numbers, then A is said to be less than B whenever B minus A belongs to P, and A is said to be greater than B when, or the other way around, B is said to be uh, less than A whenever A minus B belong to P. And or you can define it the other way around, but we define it in terms of P, set of all positive numbers, and we say A is equal to B when A minus B is 0. Belongs to, maybe we'll write it in this notation, belongs to this set 0. So we define an order relation on this set. This is an order on the set of all real numbers. We define it using a base set P, and then we define something called an order relation, and using the order relation we have this order will be a total order on that set. That is, every element will be related, if any two elements will be related, and hence we define what when hence we pronounce what is called the law of trichotomy. Okay, so law of trichotomy governs the ordering in the set of all real numbers. Law of trichotomy states that whenever A and B are any two given real numbers, either A is less than B, or B is less than A, or A is equal to B, and exactly one of these three possibilities occur. Fine. So is there any clarification, so that we will move on to the next one? Please mention it in the chat. Shall we move on to the next one? Please don't hesitate to asked any clarifications? So shall we move on to the next one? Now, so now after defining the law of trichotomy, we are moving on into defining, into stating what we call the density of rational numbers and the density of real numbers. So what does density literally mean? It means that they are very closely packed. Fine. So consider the set of all real numbers. Now the set of all rational numbers, what by the statement density of rational numbers refers to is, it is very closely packed. That is, it is so this is actually not closely packed, but still appear. Please think of it as very closely packed. So the gaps are all the irrational numbers, and if you see the even the gaps are also very closely packed. So by the term density of rational numbers, we mean that the set of all real numbers, in the set of all real numbers, the arrangement of rational numbers is very closely packed. So how it can be proved? So we are not going deep into the proof, but let us have a geometric way of constructing it. So by density, what we do is, so if a and b are any two real numbers, any two distinct real numbers, by density we say that between any two real numbers, however small a and b can be, we will have a rational number in between a and b. We can have a rational number in between a and b. Fine. Now, so if a and b are any two real numbers, so by geometric way of construction, maybe I will do this way. So consider 0 and 1. So can you give me, we can construct obviously a rational number which is between 0 and 1. Say we will consider the midpoint. Fine. Say 1 by 2. Now, zoom in. So between 0 and 1 by 2, can we find a real number? So it is easy to construct. We will say 1 by 4. And between 1 by 2 and 1, can you construct a real number? We can. Say 3 by 4. Now between 0 and 1 by 4, can we construct a rational number? Yes. 1 by 8. Between 1 by 4 and 1 by 2, can we construct a rational number? Yes. Find the midpoint of this. So it would be 3 by 8. So between 1 by 2 and 3 by 4, can we find a rational number? Yes. It would be 5 by 8. And between 3 by 4 and 1, can we find a rational number? Yes. 7 by 8. Now we can zoom in and we can keep on constructing rational numbers. So this is a geometric way of seeing how closely the set of all rational numbers are packed in the set of all real numbers. Or else we can view this density as something like we can never say which is the immediately next number to a given particular number. Say for example, we cannot say which is the first positive, non-negative, not non-negative, positive real number. So after that is which is the immediate next number to 0. So if you say something as next immediate, say rational number. So whatever it may be, real or irrational or rational. So I am saying that you cannot say the first rational number next to 0. So if suppose you are saying something as a rational number next to 0, then there will be a distance between them and you can find the midpoint which is again a rational number. So we can keep on constructing. So by this construction, by now you can see that there are infinitely many numbers in between any two given numbers. Infinitely many rational numbers, and also you can construct irrational numbers. Fine. So by density of rational number, we mean that between any two rational number, any two real numbers, we can find a rational number. And this goes on for irrational numbers also. Okay. So now I hope everyone are clear with the density of rationals and irrationals. So shall we move on to the next one? Hello everyone. Is it visible? Is it visible now? Shall we move on to the next topic? Okay. So there is a question from Mahesh. Uh, so is density and dense are this are same? Okay. So good question. So we define densities only after we define what is a metric space. Um, Actually, in a metric sense, yes, both are the same, but we are not considering density here. We are there's a slight difference by saying a set is dense and the density of rationals or irrationals. Here we are very specific about which set we are mentioning about. One thing, and this is by density of rational numbers, we are stressing on the importance of rational numbers and how it behaves. Both theoretically mean the same, but we are stressing on the importance of rational and irrationals here. So they are densely packed in the set of all real numbers. Hopefully, I have clarified your doubt, Mahesh. So when we move into metric spaces, dense sets will be even more clear. So now, so now let us move into the crucial part of real analysis, the very basic step without which uh, the entire real analysis system collapses. So, so to give a motivation on that, to give an introduction on that, we will define what is a bounded set. Now, so you have a real number line. So consider A to be a non-empty subset of R. So it will be somewhere on this real line. Now, say for example, your A is somewhere here. Now we say that this subset is bounded above if we can find an element, one element to the right of this set. This set, by what you know, this need not be an interval or anything. This can be a any non-empty subset of R. Now, if we can find at least one element to the right of every element of this set. So for every element, consider all the elements. If suppose there is at least one element which is to the right of every element in this set. Please be careful with what I say. Please listen carefully. If we can find at least one element which is to the right of every element in this set, then we call this set to be bounded above, and this number which is to the right of every element in this set is called the upper bound for this set. That is, A is said to be bounded above if there exists some alpha in R such that given any h in A, h must be less than or equal to alpha. So I write it in a hierarchical way. That is, I can find one alpha. This alpha will work out for every h here, such that h will be less. What will be true? H will be less than or equal to alpha. And this alpha is called an upper bound. So if alpha is an upper bound, any number bigger than alpha will be an upper bound, because any number bigger than that will be to the right of this alpha, and hence it will be to the right of every element in the set. Clear? So similarly, we define what is a, when do you say a subset is said to be bounded below? So a subset, a non-empty subset of R is said to be bounded below if we can find at least one element which is to the left of every element in the set. That is, this element will be to the left of every element in this set. So A is said to be bounded below if there exists some beta in R. We can find at least one real number such that given any h in A, beta must be less than or equal to x. So this beta, or the upper bound or the lower bound you find, can very well be in the set. It need not be outside the set, and it need not be inside the set. It can be anywhere. Fine. So a subset is said to be bounded below if we can find at least one such beta, and any number lesser than beta will be a lower bound. Beta will be called the lower bound, and any number lesser than beta will definitely be a lower bound. Now, if a set is both bounded above and bounded below, if a set, a non-empty subset of R, if it is both bounded above and bounded below, that is, if we can find at least one upper bound and one lower bound, then A is said to be bounded. Bounded above and bounded below. If both are true, then the subset is said to be bounded. Right? So let us see few subsets of R which is bounded above. We will try to find an upper bound. Then we will see what bounded below. We will see a few examples and then move into what we call the, then we define what is the least upper bound and greatest bound. So now consider A to be set of all natural numbers. No, we will consider this set. Set of all 1, 2, 100, 10 power 19. So consider A to be this set. We will move on slowly. Let us consider a finite set. Now, can we find one element which is bigger than every element in this set? So obviously one choice for this is I can take 10 power 20. Simple. Because it is bigger than 1, bigger than 2, bigger than 100 and obviously bigger than 10 power 90. And a number smaller than every element in the set is 0. I can choose any negative number. Fine. So these are just one possibility. There might be many upper bounds and many lower bounds. I have taken my upper bound to be 10 power 20 and lower bound to be 0. So since it has both upper bound and lower bound, definitely this set is bounded. Now, set of all natural numbers. Okay, we will try to view it geometrically and later we will try to prove. So consider the set of all natural numbers. Say it starts from 1, 2, 3, 4, it goes on. And here these are the only numbers in this set. Now you need to find one number to find a lower bound. You need to find at least one number which is less than, that is, which is to the left of every number in this number line. So an obvious choice is 0. So you have definitely found a lower bound to be 0 because 0 is lesser than any natural number. Now geometrically, by the definition of number line which you have given, it is clear that we cannot find a number which is to the right of every number in this set. That is, if you think of a number which is bigger than any natural number, I can just add 1 to it or find or do some calculation so that you can get a natural number which is bigger than that. Say if you feel 1 crore is the biggest possible element, I can choose 2 crore to be even more bigger than this. So whatever we do, we just add, if you choose a rational number or some other number to be an upper bound, we can easily manipulate it and get a natural number which is bigger than the given number. So this is possible to visualize for now, but we will try to prove it later. So it does not have a no upper bound. There is no upper bound for this set. So the set of all natural numbers is bounded below but not bounded above. Bounded below, not bounded above. So similarly, you can define the set of all set A to be negative integers. So clearly this set is bounded above but not bounded below. Now if we consider the set of all integers as your set, then definitely it is not bounded above. It is neither bounded above nor bounded below. Okay. So we will define what is the least upper bound and greatest lower bound now. So if you have any sets for which you need to check whether it is bounded above or bounded below, or if you have any other clarifications, please mention it in the chat so that you can discuss now. So if you have any clarifications, please clarify it in the chat. So if you need any examples or any set for which you need to find whether it is bounded above or bounded below, please do mention. Now, okay. So I think hopefully we can move on. So there is a question from Mahesh. What about empty set? Okay, fine. So if you look at the definition carefully, whenever we defined bounded above or bounded below, we defined it for non-empty set by definition. So we said a non-empty set is said to be bounded above, or a non-empty subset is said to be bounded below, because there is actually no element in an empty set, and hence we cannot say this is bigger than or this is smaller than. We cannot, by chance, we cannot say they are. There is an element which is bigger than this, or there is an element smaller than this, because there is no such element in the set, and hence we don't define what is an upper bound or lower bound for an empty set. Later, for computational purposes, we will define something else for empty set, which is called even supremum and infimum. But for now, we define a set to be bounded above or bounded below only for non-empty sets, not for empty sets. Okay. So now let us move into the next topic, least upper bound. And analogously, we will define what is the greatest lower bound. Now, when we define the upper bound, if you look at the definition carefully, what we said was, let A be any non-empty subset, and if you can find one element to the right of every element in this set, we call that element to be an upper bound. Now, there was one another observation which we made, that is, any element bigger than that is going to be an upper bound. So what we do is, we collect all such upper bounds of a given particular set. So given as non-empty set, if we can find at least one upper bound, there are many other upper bounds for the same given set. That is, any number to the right of that number is going to be an upper bound for the given set. So what we do is, we collect all possible upper bounds for this set, and among all those possible upper bound, there will be a least number which is acting as an upper bound. So that is a number which is an upper bound, and among all the upper bounds, it must be the smallest possible. We define that element to be the least upper bound of the subset. That is, we will write the definition properly. We can define it in two other ways. So alpha is said to be least upper bound of A, where A is non-empty, A is a subset of R. If alpha is defined to be least upper bound of A, when alpha must be upper bound of A. That is the first property it should satisfy. And the second one is, if beta belongs to R such that beta is lesser than alpha, then beta is not an upper bound for A. That is, So we are defining it in another sense, that is, if you take any number which is smaller than this alpha, it will not act as an upper bound. So if we say this is our alpha, we can find at least one number. Say if suppose there is an element here, then there is at least one element which is lesser than this. So this cannot act as the least upper bound for this set. Consider this to be our set. There is at least one element here which is lesser than this. So this cannot act as the least upper bound, because what we define the least upper bound to be, among all possible upper bounds, it must be the least possible one. So there must be no number which is lesser than this which acts as an upper bound. So that is how we define the least upper bound to be. Now analogously, we define what we call as the greatest lower bound. So A is a non-empty subset of R and A is subset of R. Okay, fine. Sorry for missing an hypothesis. To define least upper bound, A must be a subset which is bounded above. Sorry for missing this. So this is actually not necessary, because by stating alpha to be an upper bound, we say that the subset is bounded above, but it is better to mention it. So by greatest lower bound, we say that, say, beta is called the greatest lower bound of A when beta is lower bound of A, and if some C is less than beta, C belongs to R, not C less than beta, C greater than beta. Sorry. If C is greater than beta and C belongs to R, C is not lower bound of A. That is, here we define it in the other way around. So if you consider this number line, if you take this to be the lower bound, any number greater than that must not be a lower bound. That is, among all possible lower bounds, we consider the greatest one. Okay, fine. Now there is a question. So there is a question from Mahesh. Okay. Why do we check for every element? Why can't we check for the largest number in the cell? Okay, this is a very good question. There is this question arises for many people. So now I will give an example where we will find the least upper bound and the greatest lower bound. There you will see why this method does not work. Okay. Now consider the set to be open interval 0, 1. Now, so how do we define this set? This is the set of all real numbers where x is greater than 0 and x is less than 1. Fine. Now, so if you consider the number line, this will be 0 and this will be 1. This set consists of all numbers between 0 and 1, excluding 0 and 1. So you can be very careful. Here we are excluding 0 and 1. Now, we try to find the upper bound and hence the least upper bound, lower bound and hence the greatest lower bound. Now, can we say a largest element of this set? Can we try to find the largest element of this set? If you say the largest element is this, say some A, then I can find an element which is bigger than A but lesser than 1 and hence it belongs to this set. I can find the element to be this. That is, I can find the midpoint between, say, for example, now if you say A is the largest element in open 0, 1, I can find what we call as A plus 1 by 2. That is midpoint of A and 1, which is going to be lying between A and 1 and hence it is going to be bigger than A. And also it is going to be in the set. Now if you say A plus 1 by 2 is the largest element, I can find midpoint between A plus 1 by 2 and 1. So if we keep on doing this, we don't end at a particular place. It goes on. So you cannot say given any interval. This is not just for open 0 1. Given any interval, you cannot say which is the smallest element and which is the largest element. Actually, since we cannot define which is the smallest element and largest element, we try to define something which is in a way similar to that, but not exactly. So that is what is the least upper bound and greatest lower bound does. So now consider the set open 0 1. Obviously, any number greater than 1 is going to be an upper bound. Any number greater than 1 and including 1 actually. So any number in closed interval 1 comma infinity, any number in this set is going to be an upper bound for open 0 comma 1. Now among all the upper bounds, we are going to find the least possible. Fine. Now by definition 1 is an upper bound. So if you look at it geometrically, if I take any number which is less than 1, sorry, if we take any number which is lesser than 1, say it can lie anywhere here. If we take any number which is very near and lesser than 1, we can clearly see that it falls into the set open 0 comma 1. Now, if suppose by any number lesser than 1 is not going to be an upper bound for A, we can do is we can find the distance between midpoint between the given number and 1, and so that there is a number bigger than that. So maybe I will geometrically explain this. So you can consider this 1. So if you find any number lesser than this, even it can be very close to this, say some A. Now I can clearly find A plus 1 by 2, which is between A and 1. Also, I can find A plus 1 by 2, which is very close to very less than 1, but which is inside the set. So this A cannot act as the upper bound. This is not bigger than every element in the given set. So I cannot say this A is an upper bound. So given any number lesser than this, I can say that A is not an upper bound for the set. Also, 1 is an upper bound for the set. So by the definition of least upper bound, 1 is the least upper bound for the given set. Since we have shown that 1 is the upper bound and any number lesser than 1 cannot be an upper bound, so 1 will be the least upper bound. Similarly, we can easily see that 0 is the greatest lower bound for this set. Now, I will state a very important axiom and I will wind up, which is called the least upper bound axiom, which is very crucial for real analysis to survive, at least according to me. So by least upper bound axiom, what we mean is this axiom makes the real line complete. That is, you can move on in the real line without any holes in between. This is given by the least upper bound axiom. So maybe my terminologies might not be very much clear to you now, but when I state it, you may try to understand it later. So by least upper bound axiom, what we mean is, let A be a non-empty subset of R such that A is bounded above. Then A has a least upper bound in R. So there are many crucial points in this statement. So what this statement says is, let A be any non-empty subset of R which is bounded above. That is, you can find one upper bound at least. Now, given an upper bound for any subset of real numbers, what is the guarantee that the least possible upper bound, that is the least upper bound, exists? And what is the possibility that, what is the guarantee that the least upper bound which we found lies in real numbers, lies in the set which we consider? I should say it in a more abstract way, because we will see one example where it fails. So this least upper bound axiom gives us the guarantee that given any subset of R which is non-empty and bounded above, we can find an element in the set of all real numbers which is the least upper bound for the given set. And this is an axiom which is a governing rule. It is a rule, it is an axiom. It is not yet been proved, and this is the base for every other property which we do in real analysis. Now, to understand the importance of this axiom, so it may appear trivial to you, because given any set, given any set which is bounded above, you will have an upper bound. Among all the upper bound, there will be a least one. Yes, but this statement, when I replace R by Q, fails. This is not true in set of all rational numbers. That is, if A is a non-empty subset of R, which is A is a non-empty subset of Q, which is bounded above in Q, then A need not have a least upper bound in Q. We will see to it. So maybe you can check at home. I will give you a set. You can try to find what is the least upper bound, and you can clearly see that this fails in Q. So what we do is, we consider this set A to be 1, 1.4, 1.41, 1.414. Hopefully you can guess what will be the next element. That is, we are considering the decimal places of the number what we call as root 2. So we are writing the decimal expansion. We are keeping on writing it. Now this set is obviously bounded above by 2, because every number is going to be 1 point something, etc. So it is going to be bounded above by a rational number. So if you can clearly see that the least upper bound for this set is root 2, which is not a rational number. So given a non-empty subset which is bounded above in Q, it need not have the least upper bound in Q itself. So this property fails in the set of all rational numbers, but this property holds good in the set of all real numbers, and which helps us to prove many other results in real analysis. And hence this least upper bound axiom is very much crucial to learn. Not advanced real analysis, even basic real analysis depends upon this least upper bound axiom. So I think I will wind up here. So if you have any clarifications regarding this, you can let me know in the chat. So if you have any clarifications, please let me know in the chat. So is there any clarifications? Okay, so I think we can wind up here. We will meet soon again in one another class of real analysis. Thank you.